Welcome, Stephanie.
Thanks.
It's a pleasure to have you here. Like we were just chatting, this is not your first time here. So you spent a summer here as a research intern.
Yes, many years ago in 2012.
Yeah.
I had a good summer, and I'm just recognizing the building and remembering.
Yeah, it's kind of almost like a rite of passage, right? It's amazing to see how many prominent researchers in our field at one point or another have passed through an internship in this or one of the other labs.
Yeah, this is actually what I got to know then. Like, oh, these other people also have interned in the same lab back in the day.
So of course that was not. That was still not a very early point in your machine learning research career. You've been doing machine learning research for a while. If I remember, we crossed paths, I think it was 2006 in Tübingen.
Yes.
When we were both undergrads. Right, and so tell us a little bit about, like, how did you get, it's, I guess, maybe more common these days, but it was not very typical at that time for undergrads to get started in research, and especially in machine learning research. So what made you get into machine learning research as an undergrad at that point?
Yeah, that's kind of an interesting story with lots of coincidences. So I think I started hearing about machine learning when I was actually an exchange student at UT Austin.
I see.
Back when I was an undergrad. And so I took some courses there, and I took a data mining course. And I actually enjoyed that course. That's where maybe first time I heard about clustering and such kinds of things. And then I did a research project actually on neural networks and computational neuroscience. And then back when I was at home, I needed a bachelor's thesis project. And that time I had roommates who were research assistants at Max Planck Institute.
Oh, I see.
And so I was like, hey, it sounds really cool what they're doing, and it sounds very interesting, and also a bit more towards the mathematical side and algorithmic side, and I kind of enjoyed that. So it's like, hey, is there maybe someone I could ask for a project? So I asked if they have a project for me for bachelor's thesis, so that's how it started.
So I guess the fact that you were actually doing your undergrad in Tübingen, which was like this machine learning powerhouse, already at that time probably played some part.
Yes, I think so. And then some random coincidences of having met people who said, like, I'm doing this and that, and I thought that's really interesting. And then I just stuck with it, essentially. So I started working actually on independent component analysis and matrix approximations, and I continued working on that and then expanded to other topics. That's how it happened.
Yeah, so let's talk a little bit about that, right? You've had a pretty interesting kind of arc in terms of the variety of research topics you've pursued. You started, like you mentioned, with algorithms for independent component analysis type things. You worked a fair bit on clustering during your PhD. And then it seems like you got interested in discrete optimization, and just the body of research kind of exploded from there. At least that's the impression we get from the outside. So how did you get interested in this discrete optimization, and maybe just for people who might watch this conversation, maybe also tell us a little bit about what discrete optimization is, and where it comes up and how it interested you.
Yeah, so I've always been interested in algorithms. That was kind of one of the fun things I enjoyed. So actually the way I got into discrete optimization was partially I was working on clustering, and that is one specific discrete optimization problem, meaning I have data points, I need to assign them into clusters, so I have to partition them. So there's a discrete solution, and I have some objective function that I want to optimize. But then, of course, there's many other discrete optimization problems, meaning I have usually some binary variables, and I want to optimize over those variables. For example, doing assignments, finding maybe clusters or paths in graphs. Usually this involves graphs or sets or partitions, something along these lines. And where does it come up in machine learning? In many places. So one is in clustering. There's many places where, say, I want to select data points, maybe I want to do exploration, I want to see which measurements should I take to gain as much information as possible about the world. And also in inference problems, when I want to make discrete predictions. So one classical example that time was predicting where in an image is an object. So I basically make a prediction for each pixel in the image of 0 or 1, is it foreground or background. So it's an inference problem where I'm making predictions over discrete variables. And there's many other problems where maybe I want to do predictions over graphs or networks. I want to find communities. I want to find discrete labels somewhere. All of these are essentially discrete optimization problems.
Mm-hmm.
So the interesting thing is that typically computationally these can be very hard. So typically I have some kind of objective function that I want to optimize. And this can be NP hard, meaning it's hard to find any algorithm that works in polynomial time. But now sometimes they have specific structure. And so what I was interested in that time was a specific type of structure that enables good algorithms, good approximations. And that structure is called submodularity. So the idea of submodularity is that I have diminishing returns. So if I think, for example, about information, I want to find a set of items that maximizes the information that I get from them. If I have a set of items, I add one more item to the set, how much does my value or objective increase? And the more I have, the less it increases from this one additional item. That's the idea of submodularity, this diminishing returns. It's
Right.
pretty simple and hence it applies widely, but it's very useful algorithmically. And it has very nice connections to convex optimization, greedy algorithms, combinatorial optimization.
So speaking of kind of more continuous optimization and connections, so in terms of like the touch points between the broader optimization community and the machine learning community, definitely there's been like over the last decade a huge growth of that literature in the continuous optimization area. And there, partly it was fueled due to this aspect that when we started thinking about the kinds of optimization problems that arise in machine learning, they were maybe introducing some structures that were not necessarily seen before, or maybe some regimes of parameters, data sizes, things like that, that were not necessarily explored enough in the optimization literature, and that kind of led to the mushrooming of different algorithmic styles and what people were studying. Now, when you look to, again, like discrete optimization, it's obviously not a young field. It's field that has that has very rich, very old literature, both in mathematics and theoretical computer science, amongst other areas. Where has machine learning kind of influenced or changed the narrative in that field, or why is it? Has machine learning kind of added an interesting dimension there in a similar manner?
Yes, I think so too. So one is that machine learning has also brought new problems, like different clustering problems or different inference problems where I want to make predictions, structured predictions or so that lead to new optimization problems. But the other one is that maybe the focus shift. So if you think about the classical combinatorial optimization community, theoretical computer science, the main goal was to get a polynomial time algorithm for something. So
Right.
it could be like something that scales on the 5th or 6th order with like the input, but it's polynomial time. In machine learning, you care also about like even linear can sometimes be very expensive, and quadratic is also very, very expensive. So it's a completely different shift. And there maybe you're okay to have a bit of an approximation, but to be much, much faster.
Right.
So then the question is like, is there some trade-off in between? That is one question. And the other one is, even if I have a polynomial time algorithm and it's a good algorithm, it's maybe not fast enough. So one example that's maybe very easy to understand is the greedy algorithm. So one way to do submodular optimization is to run a greedy algorithm, meaning I'm picking out of the many items I have, I'm picking one item that's the most valuable, and then I'm picking the next item as the best augmentation to that set. And I do this over and over until I have k items if I want to select k. So that's a very simple algorithm. It works very well in practice. And it works very well if your data set is not too large. But if your data set is large, then searching through all these many different items, every time you augment your data set is very expensive.
Right.
So now there are new questions. Can I accelerate this? And how much do I have to trade off the quality of my solution for speed? Can I parallelize this? This is inherently sequential. Maybe I can parallelize it.
Right.
Or can I do like subsampling? So one recent line of work has looked at like how parallel can I actually make these queries to not lose the approximation guarantees that I had.
This is the work from Harvard.
This is the work on adaptivity. There's
Right.
been many recent papers, like especially from Harvard, but also other groups.
Right.
Yeah, so this is one question that is motivated by looking at submodularity on larger data sets. And there have been earlier works that used other ideas, such as just subsampling your data, how much do you have to subsample, and just doing the optimization over that smaller set of
Right.
items. Or just using submodularity itself to do a better organization of your data, that you don't have to query everything. So there's been several ideas. All of these are very interesting. And then there's also another literature just on streaming algorithms for greedy and so on and so forth. So all of this essentially was motivated or fueled by saying, I have large data sets in machine learning. Can I somehow run these methods on large data sets because they work well in practice?
And in terms of the communities, like does the discrete optimization research in machine learning and the discrete optimization research in, say, theoretical computer science or in math and other disciplines, are they at the point where they talk to each other and learn from each other, or are they still happening mostly like in their own ecosystems?
I think they're increasingly talking to each other. So there's still like theory conferences and there's the machine learning conferences, but more and more you see people actually collaborate in that space. And theoretical computer science researchers actually starting to publish at the machine learning conferences.
Right.
Another example is that even mathematicians are starting to look into problems that are interesting for machine learning. So another example is, so I recently also got interested in discrete probability and distributions that are essentially log submodular distributions and a sort of stricter version of these. And that has a lot of mathematics and algebra in this, and I know that mathematicians are starting to look at like, hey, actually sampling is a problem that's interesting for machine learning too. So there's a new dimension and new interesting directions for those people as well, and looking at, okay, what distributions are these people interested in, and vice versa, as the machine learning researchers learning from these people too.
And now, of course, a lot of the concerns you're pointing out, which are leading to these new quests for theoretical research, are very motivated from concrete applications. I know in your own work, you've always kind of maintained a thrust for also doing research in those applications. So tell us a little bit about some of your applied work, and how do you, like, often people complain about the fact that there is theory but it has little bearing to do on what's going on in practice, and vice versa. So in your experience, as you're working on better algorithms from a theoretical standpoint, and you're also working on just trying to get the best performing algorithm in the context of some computer vision problem, like how easy do you find progress in one maps to the other?
So I would say sometimes there's a discrepancy and sometimes they actually come together very nicely, and it's I like to think about things like then from a theoretical perspective, trying to motivate. So I think a very good example is my first paper in computer vision. So that time it was a very classical problem of segmenting images, basically finding foreground and background, super well studied, lots of research work on this, and I had never written a computer vision paper. So I had this idea of like, well, one problem with these methods that time was that they basically were essentially penalizing the length of the boundary of an object. And I said, well, maybe we can relieve this by instead saying I want to input some priors that the boundary of the object is coherent, so we can implement this via some other mathematical tools, so the submodularity tools I was mentioning. And I had an approximation algorithm for that, which actually solved the problem. Approximately, of course.
Right.
So I just tried it. And after a little bit of trying, basically finding the right parameter range, it actually worked quite well. So I said, well, let's submit it to a computer vision conference. And I remember that time there was another PhD student in our lab, and I showed him the results. I said, like, what do you think of this? And he was like, wow, this actually seems to work. So I submitted it, and it was selected for an oral presentation at that time. So actually that was completely motivated from an idea coming from the theoretical research, which was accepted by the researchers in the application field at that time. So that's one example that it can actually work quite well. I think nowadays also a lot of theoretical research is inspired by looking at phenomena that people have observed in practice, especially a lot of the work on theory of deep learning, trying to explain that behavior. That's another route that's also fruitful. There's sometimes still like a gap between what you can actually prove and what is actually the real model, which is decreasing. But in general, I think it's a very good perspective to think about at least like what theoretical tools I have. It doesn't always work as smoothly as that first paper I mentioned. Often it needs much more engineering to actually make something work in practice. So that was maybe a lucky case where not much of that was required.
So speaking of like trying to explain some of the properties of deep learning from a theoretical standpoint, I noticed that's what you're going to be talking to us about in your seminar today, and you've been working in this area more recently. So what are the kinds of questions you're studying in this domain?
So yeah, what I'll talk about today is a specific class of deep neural networks that actually applies to a combinatorial object, so graphs and networks. So in many learning problems, what we want is to actually make predictions on inputs that are graphs or networks, either to just put a label on a graph, say I have a molecule that I can model as a graph, I have some information about what are the nodes and maybe the edges, the bonds and the atoms essentially, and I want to predict properties of this molecule. Or I have a social network, I want to make predictions about the nodes in that network. Could also be another network of interactions. This is used for recommender systems when people click on items, or interactions between drugs or so. So what I need is a good representation both for nodes and of the entire graph itself. And this has been a field of research for long. People have long thought about how can I best find a good vector representation of graphs. And more recently, what people are doing is neural networks, which are essentially learnable representations. The way they work is they essentially find a representation for neighborhoods of each node, and then they put them together into a representation of the full graph. And so what we have been interested in is more theoretical properties of these networks. So one question I'll be talking about is, what is the discriminative power of these networks? So meaning, if I give it two different graphs, will it always map them to different vector representations or sometimes to the same one? And the problem is that if you map them to the same representation, you can never learn to assign different labels to these graphs.
Right.
So there's like an implicit restriction in what kinds of functions you can learn. And we are studying this from basically the perspective of what choices you make when you design this neural network architecture. And what you can show is basically there's a limit to how much they can discriminate. So there will, like in the current architectures, these so-called aggregation-based architectures that people use, there's always a limit on what you can discriminate, and the limit is a popular graph isomorphism test.
I see.
It's called the Weiss-Feidel-Lehmann test. And now the question is, do all the neural networks that people are using actually possibly achieve that limit? Or are they weaker than that?
Right.
And it turns out that actually some of the popular architectures are much weaker than that. And you can see this by studying like what are the aggregation functions. I should maybe explain what the aggregation is. So the way these neural networks work is that for every node, it looks at the neighbors in the graph and collects information from the neighbors, basically the feature vectors of the neighbors, combines them in some way to get a new representation of itself. So now this combine the neighbors operation is the aggregation operation. And there's a few restrictions. So for example, it has to be permutation invariant because there's no natural ordering of like this is neighbor number 1 or 2. And the other one is that you're using the same kind of aggregation operation on each node to reduce the number of parameters. And hence this neighborhood aggregation has to be invariant to how many neighbors you have, because not every node has the same number of neighbors. So these are the restrictions. And typically the way they work is that you apply some transformations of the neighbors and then you do an aggregation maybe a sum or a mean or a max pooling, and then you do another nonlinearity, and you do this over and over again. So these aggregation operations, there are some conditions on these under which you are more or less discriminative. And at the end of the day, it boils down to an injectivity condition on so-called multi-set functions. So injectivity means different inputs lead to different outputs.
Right.
And multi-set means that the functions you're actually having here get sets as inputs. This is a set of neighbors, and the neighbors can repeat. And the number of neighbors with a specific label is important, so you need to actually preserve the information about that. And that helps you. And you see actually in practice also, so this is the theory.
Right.
Now the question is what is the implications in practice. So you actually do see that the networks that respect these injectivity conditions do fit the training data better and also generalize better. So the generalization is a phenomenon we don't explain in this paper, but it happens. But you basically fit the training data much better. So it actually does have an effect also in practice. So this is one question we had looked at. There's others. For example, there's an interplay between the structure of the graph and the depth of the network that works well for these graphs.
I see.
So there's a way to explain these interactions. And you also see again in practice that there does seem to be this phenomenon happening. And more recently, we've been looking at how the structure of the network aligns with the structure of the task that you're trying to do. So this pertains mostly to questions of reasoning, where the answer is also kind of like actually computed by an algorithm, and the network essentially has to learn to execute that algorithm.
Right.
So there's also some interesting theoretical questions that you actually see reflected in experiments too.
So I guess does this way of thinking about the architectures which are better or worse for capturing the data, does it also give any intuitions for in terms of algorithm design for the underlying optimization that we need to solve, or is that still being done in basically using the same SGD style algorithms, or are there any other tricks we get to bring from the theoretical underpinning?
So that's something we are currently looking at.
Okay.
I think there's lots of open questions there. I don't have an answer yet,
Okay.
but it's a very good question. Yeah, so basically looking more at like how the structure actually relates to the algorithm that you're solving. And I think there are interactions there, and there's things you can exploit and explain probably, but I don't have a good answer yet.
Okay, we'll look forward to maybe learning about it in the next conferences. We have you here for a distinguished seminar today, but you and I, both of us, have, of course, quite a long ways to go still in our research careers, hopefully. And I'm very curious. You've like the nature of problems that you've been studying has really kind of become richer and more diverse as it naturally does over the years. Really long term, what's something that kind of drives you, that you would like to get to in terms of research goals?
I think I have a few goals that are interrelated. So one of my goals is basically to improve machine learning with structured objects. So all the discrete optimization of trying to do inferences and predictions with sets and partitions is related to that. The graph neural networks are related to that, and basically trying to get better at like the computational hurdles that are there, and better understanding the models and their properties, and understanding the algorithms, understanding like how we can do basically how we can get algorithms that we understand how they work and why they work and when they don't work, and that are actually practically applicable. So that is like one thing. The other one that we started working on is to make machine learning more reliable. That like of course relates to understanding what your models can and cannot do, and like what your algorithms can and cannot do, and to actually use specific optimization. Like, so we had looked at robust optimization.
Right.
How you can, like, that's one way how you can actually bring that robustness into the problem that has regularizing properties, and to understand these trade-offs. So basically using prior knowledge, using structural knowledge, using like optimization formulations to guide the problem and I like there's some understanding of like how we can encode what we know and what we know about the problem domain to get better models and algorithms and then a better optimization strategy. So that's like one big set of interrelated goals.
Yeah, that seems like it'll keep you busy for a while.
Oh, yes.
Now, you've also had, this experience of two very different educational systems, right? So you grew up in the European system, and now, of course, you're teaching in the American system. And I'm very curious of what you see as the relative, I would say, merits and weaknesses of the two, and I will ask you a more specific question about that in a moment, but I first just want to hear your general impressions.
Okay. Oh, that's a very big question. So yes, I did my undergraduate and graduate studies in Europe. At that time, I would say my PhD program was a bit special. It is less so than what typically now is done in Europe. It's basically, I did my master's degree and then I only did research after that.
Right.
So it's and it was only a few years, like only 3 to 4 years, versus in the US, you do your bachelor's and then you start research and you spend much more time there. So these are very different systems. In between, I visited the US. So I found that what I had learned actually in the German system was very adequate to follow what was in the American system, which I was very happy about. So I think actually the education I received was very good. And also actually at that time, at least the German system was very much focused on giving you like first a broad foundation of like mathematics, etc., and then going into the technical things. Most also possibly because at that time we didn't have a degree after 2 years. After 3 years, it was actually after 5 years. So there was like a lot of time. What I think though is a bit different. So what I would say though is like that in the end, I like those PhD programs better, where you don't only do research, but you also have a few courses and you can sort of target coursework to the research that you have and sort of continuously actually adjust, like learn something else, because it's never easier to learn about something than if you actually have a course that you can take. Even if it doesn't have to be a required course, if it's just like some fun course you can take, it's just more structured. So in that respect, I think that like the more structured PhD programs, I would say, basically you get a broader exposure to different topics. So because if you just work on one thing, you sort of get more focused on what you're doing, but you see less about sort of what else is there, or like many other directions. So this is something that when I visited the US, I noticed that there's a broader exposure you can get just because maybe there's a big university behind it. And that is something that's a bit different now in Europe, but that at that time it was a bit more focused. I think the PhD programs in general are a bit different because in Europe it used to be the case that you're admitted into a program, like not into a program, but you're basically hired by the professor and that's like your advisor, versus in the US, you're admitted to the research program, so in principle you can still change advisors. It's like a bit more flexible than that, which is sometimes a good thing if you're coming in and you don't actually know what exactly you want to do, as is the case with many students.
Yes.
Even though it's good to focus soon enough.
Now, the more specific thing that I wanted to ask also was, so one of the things that, of course, we're becoming increasingly aware of, and there's a lot of desire to do something, but we don't always have good answers. Is the overall lack of diversity in STEM fields, right? And in particular, when we look at the statistics for machine learning conferences, it's pretty damning. And if you start going narrower into machine learning, you realize, sometimes in fact all of the machine learning is still maybe being, there is like a handful of areas that are maybe making all of machine learning still look good relative to what it might really be. So I was curious in terms of your own experiences in the German system, and then now what you experience what you see the students going through as a faculty, like, are there things that we can learn that we can incorporate from the German or other European systems that maybe are helpful in terms of improving the diversity in STEM fields? And what was your experience like when you were, I'm sure you had to overcome more than a handful of challenges to get to where you are. So what kept you going?
Yeah, so first, the thing is, like, I think the same problem persists in many countries, and many times also in Europe I have been the only woman.
I see.
So I'm not sure, like, there's good things to learn from either side. I think there's other countries where this is different. But I think in general, so the thing is there needs to be support, like, at multiple levels. So one thing is getting people interested in to even start, say, a college education or graduate studies in this field. So it actually needs to start, like, way early. And I remember when I was in high school and I was like saying I'm going into computer science, people were like, why do you want to do that? It was like, go into management or something, like, but computer science, that's, like, so uncool.
Oh,
So
that's not necessarily gender specific. I remember my dad. So my dad was an electrical engineer, and he was like, oh, these computers, they're done. Like, the .com boom has happened, and this is just a fad. Look, like, nobody is leaving electricity behind. You should do EE.
Yeah. Okay, so there's that one, but there's.
But I still, yes,
Yeah.
I understand what you're saying.
Just sort of the thing of, like, the thought of, like, as a woman, what are you going to? And I saw, like, all the other women were going into business or something like that, and maybe medicine or so. It was just not a typical thing to consider, and basically to change that mind. And I remember, like, I had some physics teachers who also made some remarks, etc., where I was like, yeah, I'm like, at that time. So basically, even showing people that if you want to, like, there's interesting things to discover. And I remember, like, I liked mathematics at that time, so we had this thing where, like, you could go to some advising and they would tell you, like, about what are maybe good job choices or so. So I said, like, I like math, and they were like, you could study math. I asked them, so what do you do when you study math? They were like, yeah, you can work in an insurance company, and I was like, yeah, it sounds very exciting. Like, the way they described it. So I was like, I'm not going to go into math. In the end, maybe I think I would have been happy there too, but, like, at that point no. So basically just knowing what exists, and at that time I also had no idea, like, what all you may be able to do with machine learning. I didn't even know that machine learning exists. Then, like, what is the breadth of computer science? I didn't know. I actually went for bioinformatics at that time. I was like, I like math, I like biology, I like many of the things that you do. I wasn't actually even specifically interested to do computer science, I have to admit, at that time. So that's how it evolved, and then I actually learned much more. I went into computer science studies. I didn't really know how to program. We had to do, like, a little bit at school, that was it. So at that level, like, just getting people interested is one point. And then the other one is support. So I see, like, acceptance of women in leadership positions is very different often. There are these things of, you just got this because you're a woman, kind of, like, judgments. And then the other thing is support. So, like, I see also other women who say, like, this is too much, or, like, say, being a faculty job, it's just too stressful, I don't want to do that. So there's also these kinds of things, like, apart from, like, discussions we've had about basically insulting and offending, but at different levels. So one other level of support is, for example, like, say you're a woman, you have a child. How flexible is the work experience with that? And that, I have to say, actually, I have been very lucky. So I had a child 2 years ago, and I had lots of support from the department, and I wasn't sure at that time. It's a male-dominated field, I don't know. In many cases in my career, I have been the only woman, starting from PhD student. For, like, some time, the only other woman was the person who was the administrative assistant in the office. So, I wasn't sure, but actually I was very lucky, I would say. It was a good thing that actually there was support and flexibility, and there's, like, childcare options available. Otherwise, it would be hard for me to do the job
Right,
and just
right.
follow up. And so I think if you want to support women, there's like at many dimensions. So there's the thing about like getting respect, but there's also the thing about like starting early to get people interested, just to have enough women interested in the field. If there's only
Absolutely.
2 women applying, like what can I do in like
Yes.
100 men? And the other one is to continue giving support and saying like, okay, it's actually feasible, say, to combine family and job, and all of these questions I think are important.
So one dimension of support I also kind of heard, at least, or perceived in your response, was that sometimes it's important if you have role models that you can look up to. Did you have did you have such people when you were just getting started in the field that helped you kind of overcome those initial hesitations? Or
So actually, I didn't have a female role model.
Mhm.
Frankly speaking, I think all the people I knew in the field were male. Or, I mean, at least in the more senior roles.
Yeah.
But what I did have was very good support from my advisors, people who I've been working with, who were continuously basically believed in me and had were encouraging me, and that is, I think, very important. So that there's some people who believe that you can do it, even say when things go, like paper gets rejected, etc. These things happen, and there's people who make you believe that you can do it, and that like things work out, and that is, I think, very important. So someone who gives you basically support, and that can also be a network of people. This can be role models as well. So I think it's good to have role models, but I think a very important role also is played by advisors and people
absolutely.
who, like, that you work with. If they believe in you and they give you the feeling that you're valued and you're strong, you can do it. If they give you the feeling that no, everything you do is just worthless, then I don't think you'll go very far, unless you're really, really strong as a person by yourself.
That's
No, but that is
I
maybe
completely agree.
less women-specific and more general.
Absolutely.
I'm sure this is the same
Absolutely.
for everyone.
I think we've all, over the course of our PhDs, had difficult moments where we've doubted our ability to get through things, and having a good support structure and having encouraging mentors absolutely plays a big role. And I think in particular, often we see we also see that make people hesitate when taking up more mathematical or more theoretical topics in terms of their research areas. So it's like in those, it's even, I would say, all the more important to have the right support structure. So I think we're kind of getting up on time here. Are there any final words of encouragement or wisdom about for our viewers who might just be thinking about how to get started in their research, or how to navigate this this difficult terrain that you would like to offer?
So I think for all young researchers, I would say one is be open-minded. Learn about many different things. Don't discard anything. That's a very important thing. And be courageous. Explore new things. And just have fun.
Yeah, I think the last bit often gets ignored, huh?
Yeah.
Well, it was a pleasure again, and we'll look forward to learning more technical aspects of your work in the seminar today. Thanks a lot.
Thank you.